I think we're going to get started now. So our first speaker today is Dr. Merrin Macrae. Merrin Macrae is a professor in the Department of Geography and Environmental Management at the University of Waterloo since 2006. She specializes in hydrological controls on biogeochemical processes. Her research interests center around nutrient dynamics, nitrogen, phosphorus, and water quality in agricultural landscapes and wetlands. Dr. Macrae studies water quality at both watershed and field scales, with an emphasis on understanding the impacts of assisted or modified land drainage. Her work also emphasizes the winter and snowmelt periods, characterizing the efficacy of conservation practices during these critical times. Her research is largely based on field-based science, focused in Southern Ontario and Manitoba. She's supervised or co-supervised more than 35 graduate students, 5 postdoctoral researchers, and 18 technical staff, publishing 80 peer-reviewed journal articles and co-authoring more than 230 conference presentations. She's also a frequent speaker to the farming community, industry, and government, often serving as a keynote speaker or panelist at meetings. Her work has also been featured in the agricultural media, magazines, podcasts, newspapers, 10 times over the past 8 years. Today, she'll be presenting the importance of targeting conservation practices to improve water quality. I'm very excited to have her here with us today. Thank you, Merrin, for joining us and giving us your time.
Okay, guys. So today I'm going to be talking about the importance of targeting conservation practices to improve water quality. So essentially, we're trying to target the practices that we use on our farms based on the land or the landscape that we live in. So essentially, I think I won't dwell on the Lake Erie water quality issues for a terribly long time, but essentially I think we're all quite familiar with ongoing issues related to harmful algal blooms and nuisance algal blooms, and there's a significant amount of pressure to improve obviously improve that water quality. And a lot of the blooms are being really fueled by excess phosphorus inputs from watersheds surrounding Lake Erie and in the Great Lakes region, in general. And we're also having these issues in Winnipeg and Lake Winnipeg. And the bottom line is that we know that a lot of that phosphorus is coming, not all, but a lot of that phosphorus is coming from agriculture. And so there's, like I said, a significant amount of pressure to obviously reduce these blooms. So essentially, some of the things that we can do to improve water quality basically relate to using beneficial management practices or conservation practices on our farms. The problem is, I think people sometimes struggle with, well, what do I choose? There's so many things to choose from, and there's lots of reasons why people would choose one or another, maybe related to economics or logistics, what they have the time or the ability to do. But the reality is that they may be applying certain conservation practices that may or may not be ideal for their farms. And so a lot of our knowledge around agricultural BMPs has been gleaned from really the growing season. And we really have gaps in terms of understanding how, if those same BMPs apply in winter, and basically how effective they are across different landscapes. And so oftentimes when I give presentations about conservation practices, people will say to me, what is the one thing that I can do? What's the best thing or the one best thing that I can do on my farm to improve water quality? And I know that we've all heard this before, that there is no silver bullet. And we've also heard the idea of stacking. And so stacking beneficial management practices. We know that rather than using just a single thing, if we can accumulate them by doing multiple things on one another, essentially you're going to have a higher chance or basically higher efficacy in terms of these things. So in light of this circumstance, we've said to people, there is no one silver bullet. If you want to know what to do anything you can, do anything and everything you can. And so that's kind of been some of the messaging. But then we have to realize that we're asking people to do a lot of different things. And every time they do those things, there is a cost, be it financial or logistical. There are costs associated with these every time we ask people to apply, whether it's acquiring new equipment or taking on risks, you name it. And so we can't ask people to just keep doing things and hoping that a couple of them work. We can be more strategic. And essentially, if we know that a conservation practice is going to be more effective in a given landscape type, then we should really think about emphasizing that conservation practice in that landscape type. And we also know that there are some BMPs or conservation practices that might work really well in one landscape type, but could actually have unintended consequences in another. And so we don't want people applying BMPs and then being told, oh, this is the reason why why phosphorus exports from watersheds are increasing. You don't want to have that happen. So I think what we need to do is really start to be more strategic and say, look, if you live in a particular landscape type, here are the top ones for you. And if you live in this other landscape type, here are the top ones for you. And so I'm going to give you some examples of that today. So when we start to think about regional differences in climate, we often think about, say, here versus the prairies. We think about agriculture in Saskatchewan or Winnipeg, but when we think about the Great Lakes region, we kind of think about it as sort of being the Great Lakes climate. And the reality is that even within the Great Lakes region, we have subtle differences in climate. And so what we have here are some maps of the Lake Erie watershed that are actually showing you annual precipitation. So that's, of course, the combination of rain and snow, your mean or average annual temperatures, as well as your growing degree days, but also right here, the duration of snow cover. So how many days in the winter do you actually have snow covering fields? And the fact is that if you look, we really do have a bit of a gradient where things are warmer here and they start to get cooler, especially as you get really up into the upper Grand or even in the upper Thames. And so we know that we have fewer growing degree days and we have a longer growing season. So certainly, there's definitely annual temperature shifts or seasonal or differences in seasonality of the temperatures, but also the importance of snow cover. We know that we start to get a more snow melt dominated spring melt in these situations. Whereas once we're down in here, you're going to have some snow and then you lose your snow and then you gain some snow and then you lose your snow. So they don't have that continuous cover. So what becomes really interesting about it is even though these are warmer conditions overall, what can happen is without the insulating effects of the snow cover, you actually are more prone to frozen ground down in here than you are up here because we have that blanket of snow that tends to stay for a little bit longer. So this is all important because essentially it affects the timing and the forms of precipitation, and that is going to drive how and when water leaves our fields, and we know that phosphorus moves with the water. So we also have differences in the regional landscape. So we have differences in elevation and also in soil texture, where essentially when we can look at even our geological maps, but essentially what we're seeing is that when we go to when we look sort of certainly hugging the lake, we definitely have very level or near level, also fine grained sediment material. So that's where we know you're down in the clay plain. But once you get outside of that, you start to get into more undulating or slope topography. You start to get into more coarse textured, loamy soils. And so again, what we find is that the way these soils drain differs. So we know that as we get towards the southwestern end of Lake Erie, we know that we have a lot more agricultural tile drainage. I'm getting admits that keep popping up. So I don't know if you see me admitting people willy-nilly or if you just see my PowerPoint, but it's interesting to see if I can multitask. Anyway, so yeah, there's a lot more agricultural drainage as we go towards the southwestern end of Lake Erie. So essentially we have landscape, we have a little bit of differences in our climates and a little bit of differences in our landscapes. And so this is, again, together, they're going to affect how water moves and how phosphorus moves and the timing of that, and also the pathways. Is it moving above the surface or is it more likely to go through tile drainage? And is it going to happen year round Or is it more likely to be focused in the non-growing season? How important is your snowmelt? And so what we did is we actually put all of this together and we designated different phosphorus management zones within the Lake Erie watershed. And we just did a coarse classification as a starting point. So what we found is when you were in the upper Thames and sort of in the middle to upper Grand, and even some areas in the US, you tended to have more of this sloping ground with coarser texture soils. When you were down in the southwestern end, you were more likely in a flat landscape or level or near level with more of these heavy clays. And then in the middle, we had some of these transitional areas. And so this transition area is a little bit tricky because the soil, climate-wise, it tends to be a transition between this zone and this zone. But from the soil's perspective, I would argue that sort of up high, at the higher end, they're going to be more like the Northeast, and around the lakes here, it's going to be, there's a lot more clays again as we hug the lakes. So this could be subdivided further. But essentially, we can't tell everybody to do exactly what they ought to do on their farm. But what we can do is provide some sort of general principles or general suggestions for what might be the most bang for your buck or the most effective based on where you live. And so a lot of this started because we were reading a lot of the literature, a lot of the science that was coming out of Northwestern Ohio. Farmers were hearing about and wondering if it applied to their fields. And what we're finding is that, yes, some of it does, but some of it maybe doesn't. And so I think that in our messaging, we can do a better job with explaining what is going to work in these different regions most effectively and why. So the first question has to do with how and when are water and phosphorus leaving the fields in Ontario. And so certainly there's surface runoff, but there's also tile drainage. And this is not an Ontario picture, but it's a good picture of surface runoff. So I've included it here. But essentially the orange is showing you surface runoff and the blue is showing you tile drainage. This is our Lawnsboro site, which is in an example site in terms of that sort of undulating, rolling topography, or at least sloping ground with coarse textured soils, whereas Essex, of course, is very level with those heavy clays. And so what we're finding is that when we compiled the data over a 4 or 5 year period, what we found is that in any given year, 80% of the water left in tile drainage. And often we hear farmers say, oh yeah, I don't get very much surface runoff at all. And it's true, you may not get a lot of surface runoff. It might just show up a few days per year, and the rest of the time it's all underground. The problem is that that short period of time in a given year can actually account for a substantial amount of the phosphorus that's actually leaving the fields. And this becomes most important in those sloping areas with sloping ground where erosion can happen, but also there's not a lot of phosphorus, not as much going through the tile drains because the soils seem to have a better ability to hold on to that phosphorus. Whereas once you get down into the clay plains, surface erosion can definitely happen. And so we can see that our surface runoff plays a more important role, but from a soluble reactive, so that's your dissolved reactive phosphorus, which is your bioavailable fraction, that essentially is basically proportionate to water. So the tiles really are the most significant phosphorus pathway in these landscapes. And we also can see from a seasonal perspective in terms of the growing season, the GS versus the non-growing season, that essentially that non-growing season, especially the snowmelt period, is really what is accounting for a substantial amount of those losses, especially in the case of surface runoff. So when we start to think about what are some of the things that people can do, one of the first things that we can think about is how much phosphorus is being applied, not just how much is being applied, but how and when and where it's being, when and where it's being applied and how much. So we know, this is just one example from one of our papers, but there's been lots and lots of studies, both in the Great Lakes region, but even globally, that shows that the higher your soil fertility is, the greater your phosphorus losses are going to be. And there have been studies that have shown that if we can get that for those levels down, to reasonable levels. You know, you're not asking people to go below agronomic thresholds, but if we can get those elevated soils down, it can have a considerable effect on reducing phosphorus losses at the edge of the field. So certainly applying at the right rate, so we're thinking 4 Rs here, is going to be really important. But we can't count on this alone. It can take quite a bit of time. And even if you have soils at agronomic, at reasonable levels agronomically, you can still have phosphorus losses. So that's not going to be enough. So the other thing has to do with applying phosphorus, whether or not you surface broadcast or you can get it below the ground. And so we had done some research. So this is some work that Kirsten Grant had done, where we had done some experimental work. In fact, Henry Donato, so I know who's on this call, and Bob McIntosh in St. Mary's, we had done some work looking at phosphorus application, where she applied phosphorus on the surface and she placed it in bands. So she subsurface placed the phosphorus fertilizer and then did rainfall simulations and snowmelt simulations. And what we found is that basically when you can band your phosphorus in the subsurface, you basically disconnect it from the important preferential pathways or macropores, which are what really connects that phosphorus from the surface to the tile drains. So you're essentially disconnecting the source from the primary pathways, or you're lessening it anyway. And she found that it reduced both phosphorus and nitrogen losses by about 60% over her experiment, but we actually think it's probably even higher than that. So you know, obviously you can inject it in the ground or you can incorporate it. So that I'll come back to tillage in another slide. Timing, obviously, at the time of seeding is the best, and you never want to apply on frozen ground. But the reality is that certainly because we have this pronounced snowmelt in the winter season, as you get into these colder regions, it gets harder and harder to fall apply. So if people can apply, certainly, you know, especially ahead of corn, and if anyone applies ahead of soy, essentially doing things with seed at the time in the springtime is going to be the most effective way to do this. Whereas in the southwestern end, because we don't have a terribly wet fall season and things go a little bit later, as long as you can get it on earlier in the fall, that window is a little bit wider and it doesn't seem to be as problematic. But again, winter applications should never be done. Tillage is an interesting one because that's how this really all started. There was a lot of concern about no-till, tile drains and no-till landscapes, where they were arguing that the no-till sites were in tile drain landscapes in northwestern Ohio and Indiana, but basically this is where they were saying that this was why we were seeing increased nutrient loads to Lake Erie as a consequence of this. So we had started to do some work we started out in the Lake Simcoe watershed doing some work in a sandy loam. And what we did is we had plots in a field where we had plots where they were both in no-till. So that's the okay, we had one field and another field. And then after about a year or a little over a year, we tilled up essentially one of the plots in each field and left the other one as no-till. And so when we start to think about the differences between till and no-till, look at the difference between having a high and a very low soil fertility. The fertility is going to be a bigger effect on what you're losing at the edge of the field than tillage. So it starts to think about sort of a hierarchy of things that are going to have a bigger effect versus a smaller effect. But essentially, we expected that if we tilled the fields that we would see a drop in phosphorus losses. And you know what? We didn't see it. Now, part of the reason is that this particular farmer also uses banding or subsurface placement, and it's vertical tillage. So it wasn't really a very high disturbance till. More recently, we've been working with the Lower Thames Valley Conservation Authority, and we have been working at sites in Chatham. And so what we did is we looked at basically a conventional for the region, which is an annual conservation till, and then a no-till with a cover crop. And essentially this is pretty involved, so I won't spend a lot of time on it, but essentially what we're finding at the no-till site, where things are surface broadcast in the clays, we definitely see an increase in phosphorus losses as far as the dissolved phosphorus goes. And this is especially with incidental losses following the surface broadcasting of fertilizers. But at the incorporated site, the total phosphorus and the sediment losses, so the erosion coming through tile drainage is just as much, and if anything, it's bigger. So the overall losses from the tilled site actually were greater. So the reality is that it's not simply tillage, it's the mixture of tillage with fertilizer placement. So essentially, if you're going to till, you're going to have erosional losses. If you no-till and surface broadcast, you're going to lose it all in incidental losses. So the best thing to do is essentially no-till, but with subsurface placement. And if we can combine those BMPs, this is where you're going to have a winning combination. And this is really important across the board. So essentially, this is just kind of a summary of what I've said. You know, basically the role of tillage really hinges on necessarily, you know, where you live, where essentially if you no-till and surface broadcast, it's not going to be as detrimental as it might be down here where there's so much preferential drainage. But on the other hand, tillage will increase particulates and erosion in tile drainage, but that's going to be especially important in this landscape where most of it is leaving in surface runoff. So it really, you know, it can essentially, yeah, so really, the tillage question is really an interesting one. Cover crops are the last one that I'm going to talk about essentially. So cover crops are something that have a lot of promise. We're looking at building soil health, and these photographs show you that really this is a flume at the edge of the field in a bare field versus a cover crop field. And you can see that it definitely reduces erosion. We know that they can build soil health. The problem is that there's a risk of phosphorus loss following winter freezing. So a lot of people are a little bit nervous. Am I just going to be mining the soil and then releasing all of that dissolved phosphorus at snowmelt? Well, the reality is that a lot of the evidence for that actually comes out of the Canadian prairies and also Norwegian and Swedish, you know, Norway and Sweden, where they have much colder temperatures and they don't have as much snowpack. So their crops are exposed to much colder temperatures than we do. So yes, we get cold air temperatures, but because we have so much snow in the Great Lakes region, essentially that insulates the crops. So they're not exposed to as much. Now, when you lose the snowpack, that's where they can be exposed to those frozen conditions. So what we did is we did an experiment and we looked at a more moderate frost and we looked at a more severe frost. And what we found is that yes, cover crops can release phosphorus after you freeze them, but it tends to get worse when you look at the tender species that are prone to frost kill. Whereas if you can look at more hardy species, things like rye or clover or even vetch, you're not going to lose as much even at these very cold temperatures. We also found that when you have where the fields that you have, if you have vegetation that's going to sit there steeping like tea because you have a lot of standing water for prolonged periods of time during that snowmelt period, that's where you're going to lose a lot more phosphorus than you might from, say, up here. So the reality is that yes, cover crops can release phosphorus. However, you can manage the species and the fields that you plant them in to reduce these losses. So I think all in all, in this region, cover crops are a good idea. So the key messages are that different regions have different climates and landscapes, and this can affect how phosphorus leaves the fields. And so because of this, the different conservation practices are going to differ regionally. And so looking at these phosphorus management zones are basically, we've done this to give general principles for things that are going to try to tease out where it sometimes sounds like uncertainty over the efficacy of conservation practices. It's more that sometimes they work really well under one set of conditions and not as well under another set of conditions. And we're trying to demystify that so that people can target and be very strategic with the conservation practices that they use. And with that, I thank you for your time today.
All right, thank you everyone, especially Merrin, for your wonderful presentation. We're going to move a little bit from the field, kind of following that water down into the drain with Dr. Febria's presentation. I'll let her get set up, but I'll give you a little introduction. She is a Tier 2 Canada Research Chair and an Assistant Professor at the Great Lakes Institute for Environmental Research and the Department of Integrated Biology at the University of Windsor. Her research focuses on the ecology and restoration of small streams and wetlands in human-impacted landscapes and the role of small waterways in supporting good ecosystem health in the Laurentian Great Lakes. Since 2009, she relocated her research from agricultural stream restoration in New Zealand to launch the Healthy Headwaters Lab and research team. She is the co-director of the GLEAR Organic Analysis and Nutrients Laboratory, a central research facility, and the associate director of FishCast, an NSERC Create graduate student training program. Her research has been published in journals that include Science, Environmental Science, and Technology, and Proceedings of the Royal Society. Her lab hosts an Indigenous Knowledge Circle and a farm advisory board of settler and Indigenous farmers who regularly meet to advise her team on farm and freshwater research. They are all currently partnering on a storytelling series about diverse approaches to farming. She wears many other hats relating to science and decision-making at local and global scales, including a nominated role with the UN Intergovernmental Platform on Biodiversity and Ecosystem Services. But she is also Merrin Macrae's #1 superfan. With that, I'll hand it over to Kat for her presentation on a literature synthesis of ecological impacts of best management practices in agricultural drains.
Okay, thank you. Can you hear me okay? Is that working? And the screen looks good on your end?
Yep, looks all good.
Great. Thank you very much. Good morning, everyone. Thank you for the invitation to present. And it's just such a privilege to present after Merrin, whose empirical work is, more and more we look at the literature, the team of her work is just really outstanding and relevant. So thank you so much for joining us. I wanted to first acknowledge a broad network of partnerships. So it's a perfect transition from Merrin's group, where we in our team focus on partnerships and local knowledge to inform the science that we pursue. And so I wanted to start by giving gratitude to many farmers and farm communities who have gone on a journey with us to try and figure out how we can find local solutions to some of these larger scale challenges. And these are just some of the ones that currently sit on our advisory board now or recently. Okay. So the work of the advisory board and the farming community in a freshwater team might sound kind of random, but it's intentionally where we begin. I've again spent many times and years in other agricultural settings working with farmers to find a toolbox of solutions that sit and fit in their local context. To this end, we spent a lot of time doing a lot of knowledge mobilization, trying to understand how a freshwater team and our nutrient toolbox can be of use. And we publish plain language newsletters and translation materials to explain what we're doing with soil and water data, how we're trying to connect what's happening on the land with what we're measuring in the water. This includes things like molecular tools that look at carbon and trace it as its currency from the farm field into tile drains, as well as adding just another layer of evidence, empirical evidence to this landscape where a lot of focus has been on phosphorus. We are offering data and insight into a more, what a diverse set of practices might tell us if we look at the carbon. This is intentionally part of the research we pursue. We do a very intentional relationship, but partnership-based model where we talk to many people and to try and understand where the key science gaps are that at least a freshwater team can help address. This allows us to co-create research and study designs. We talk about how to mobilize the data even in the middle of doing it. And we form partnerships, including with St. Clair, with Merrin's team, IRCA, and other conservation authorities and farming communities and people really that have a lot of experience beyond just a freshwater science that we offer. So I'm here to talk to you about one type of example partnership. So this was really through support and funding from St. Clair Conservation Authority, the Municipality of Chatham-Kent, OMAFRA, Eco-Canada, that allowed us to hire an undergraduate student from the University of Waterloo to work between our teams. We really wanted to help and assist and ask from drain superintendents around how can we, look at the drain management scheme, how can we add value, and what is the evidence on in studies around the world that have very similar context to that which we see here in our part of the Great Lakes Basin. So for the next couple of slides, I'll be talking about drain management practices, DMPs and BMPs. And I also wanted to acknowledge that a few of our co-authors are here on the call today. So what we were asked to do as the science team was to answer the question for our drain supers that how does drain management affect or benefit or impact water quality in Southwestern Ontario, given all of the different ways in which farms are managed. What is the literature on BMPs, the best management practices versus the current ones? And how can we sort of provide and generate a toolbox and the evidence to inform decision making in this agricultural landscape? So these were kind of questions that came to us through this process of partnership building. So our undergraduate student, Kirsten, conducted a systematic lit review. We actually went through a process of, we took quite a few months to make sure that we were capturing all the kinds of considerations that our drain managers and conservation authorities were interested in. The kind of data that we were able to look at spanned globally, and here's just an umbrella kind of broad look at where the papers were being published. And a lot of this work is happening here in North America or Turtle Island. We really listened to what kinds of drain management practices are currently happening at the farm field and in the drain network. We were able to uncover 91 different papers, the majority of which were empirical studies and some that were reviews of other studies. We were asked to look at different ways that water quality was being measured, different ways that flooding or sediment issues are being addressed, because there is these drains are home to biodiversity and invasive species and native species. We were asked to include any work that we could find, as well as look at sort of biodiversity indicators such as grasses and other kinds of ways that drains are being vegetated. You can see from this list that the kinds of types of DMP and management tools that we're currently under in the toolbox are there, as well as BMPs that they've either heard of or interested in pursuing across the landscape. So we really, again, focused on these management practices that our Chatham-Kent partners were interested in. And we actually also generated, a process of community peer review. So once we did this work and did the synthesis, we went through a period of circulating a white paper to our conservation authorities and drain supers for a period of 4 to 6 months, for allowing them time to give us feedback on any studies that we might have missed, any other knowledge out there, and to please send them to us so we could include them as part of our analysis. So these are just the kinds of terms that we can see what it looks like in terms of managing sort of this land-water interface. Just a couple of quick results. We're really happy to say that Kirsten submitted this for peer review, and it's sort of the last stage of review, so hopefully it'll be in your hands this year. But we did find that in general, there's greater interest in looking at studies of management practices in agricultural landscapes. We can see in the last 10 years, an exponential increase in the number of studies being pursued. In addition to that, there's also a lot of reviews of other studies. This will become interesting and pertinent later. You'll see the majority of the work are empirical studies that are looking at a combination of DMPs, which you can see in blue. This is sort of that top A panel, that pie chart. The majority of the work is focusing on the best management practices, with less focus of empirical studies looking at current drain management practices. And likewise, when we look at the ratio and the number of studies that are looking at sort of water quality indicator benefits, the majority of the focuses of studies that are happening in the recent 10 years have been focusing on the best management practice. This was an interesting result of only to illustrate and to communicate and understand that we still don't have a lot of baseline for the current existing drain management protocols published in the literature. So we really need to look again to our partnerships to see if there are data available that we can use when trying to assess the effectiveness of BMPs alone. So what are the kinds of drain management practices that are happening globally? Well, we were able to find the majority of the work is focusing on channelization and dredging. So this was, trying to make the drain function work better by either dredging out sediment that might be building up in our drain networks, as well as brushing. So trying to minimize the amount of, erosional kind of forces by doing the dredging itself. We see that there's a number of different approaches to think about replacing culverts, anything that might help reduce any sort of erosion or high, the high angles in our drains. And when we look at the number of BMPs that are being studied in the literature, we see the majority of them are really looking at controlled drainage. I'm pretty sure the majority of those studies were Merrin's and her team, looking at a range of farm agricultural BMPs, as well as wetlands, riparian buffers, and two-stage. So again, because we were looking for specific indicators, we did filter out studies that needed to be on either low gradient or similar soil types, so that which we found in soil in Southern Ontario. So that's one of the reasons why some of the studies that we could have seen elsewhere were filtered out, because again, we wanted to make it relevant to our community practitioners. All right, so what did we find in general? What's really interesting is that regardless of a current existing drain management practice or a best one, the monitoring time is very limited. This is very interesting because we know that things like, soil and nutrient processes, there are some, interannual and longer term processes that we're not capturing when we're doing short-term studies. The majority of the focus of studies are really focusing on sediment loads, nutrients, and phosphorus. But what was interesting is that they weren't all measured in the same way, which made it really difficult for us to actually compare in and out or percent removed across the board. We did see when we did have sediment load studies, there was a reported reduction in oxygen, which is not surprising, but this obviously has an influence on the fact that these drains also support critical fish communities. We did see temperature benefits that arise when you have some overhanging vegetation. And that, we do see that a lot of the kind of things we're seeing locally has been echoed in the literature, that some maintenance of vegetation is essential, and looking to other kind of best management practices, maybe as a tool or stacked in what Merrin talked about earlier, may allow a number of different functions to be supported that include things like flood mitigation and nutrient retention. And so the BMP results were very similar, where we're still seeing really short monitoring periods. We did see some evidence that things like a two-stage channel or things where we can have some artificial floodplains that create some form of a tool that can allow organic matter to build up can offer an additional nutrient retention. We found that some cost benefit analysis shows that some of these BMPs might be more expensive, but they do stabilize over time. Again, this is echoing what Merrin's empirical research is showing us, that edge of field work offers additional benefits, but really needs to look in combination with other tools and over the long term. So what I'm hoping this helps emphasize with Merrin's talk is that we really need to assess the implementation of these, thinking about their locations and ages. Bringing together water quality and biomonitoring data sets have been a very fruitful activity for us to try and build as much information we have about a specific setting. And we really have benefited from engaging other supers and drain supers and conservation authorities about the data that are already out there to help inform local decision making. We do know that there is a consideration of trade-offs. And so again, the clearest thing and the role we can play is to try and offer that monitoring so that conversations about what those trade-offs can go on. But the key is we need to move forward. And so this is some of the examples of the kind of drain activities we had observed. So as part of the synthesis, Kirsten spent half of her time with the municipality of Chatham-Kent, observing the different practices, really thinking about local context, and engaging in dialogue with different people who would be able to use this information. And that included individual farmers as well as different conservation authorities. This really helps bolster some of our place-based work, which is, again, I'm hoping in complement to some of the additional work where we are using some of our tools that we use for water quality at the land-water interface. So again, we know that there are lots of conversations about phosphorus, but we really wanted to make visible what is carbon doing across the landscape. Now, what Merrin talked about today was thinking about cover crops and tillage as in comparison to conventional agriculture. And through our partnerships with our Farm Advisory Board, we've been able to knit together a broader gradient that extends to include some additional forms of tillage, so conservation tillage plus cover crop combinations, as well as forests here in Essex region that was previously agricultural land that was around 50 to 75 years old. So by looking at our carbon indicators, we've been able to look at from surface to subsurface carbon in the soil. And what Lauren's thesis has shown, and her work is still under, she defended her master's, but she was able to show that we see the greatest accumulation of the humic carbon, which farmers are wanting to see in the top layer, especially in this low gradient clay plain landscape. And that the significant difference wasn't necessarily between a no-till and till site that's been 20 years. We were seeing the greatest difference between our agriculturally reforested site that was maybe 50 to 75 years old and our different tillage versus non-tillage examples. I think what this tells us is a bit of a reality check of how long it might take to accumulate the kinds of carbon we're wanting to see in the soil types that we're looking at. But we are starting to see evidence of things like the presence of wetlands, which we are monitoring, potentially offering a mechanism for encouraging greater carbon sequestration. So we're looking at these agricultural wetlands now, doing empirical work on them, some that are newly constructed and some that are older, not only looking at the water quality and soil benefits, but also looking at the vegetational biodiversity to explore what those relationships are. Again, making visible the potential benefits and trade-offs with different tools that might be available to our farming communities. And I just wanted to acknowledge the students that have been doing all of this field work for the last couple of years. And of course, in the St. Clair River watershed, we can't overlook the partnerships and the incredible biodiversity that's available that we're finding in this watershed compared to other watersheds in southwestern Ontario. So we do work in partnership again to try and inform and help farmers and conservation authorities on the ground to understand the relationships between things like water quality, land use, and species at risk. And our master's student, Roland, has shown really high levels of significance between benthic invertebrates and species at risk, all in this agricultural landscape. So we can't have conversations without thinking about the other. I wanted to end by simply saying that I wanted to echo what Merrin has just said, that the best way we can move forward is together, and that partnerships to allow us to overcome a lot of the barriers of scale and resources. And this is really lived experience that I've had the privilege to learn myself by working for over 5 years with agricultural farmers in New Zealand. We were able to work at the catchment level to when one farmer had a wetland and another person was doing sediment traps, we were able to monitor them in coordination. And we were able to leverage resources to enable this work to happen for multiple years. And so I've presented this work before, but I know it's very often we don't think that a place like this has anything in common with New Zealand, but we are working in landscapes and we can learn from other places like the Netherlands, like lowland Canterbury, where we have low gradient farming happening and clay soils. And so one of the kind of new learnings we've seen is that a PhD student that was looking at trying to find a way to alleviate the need for drainage and sediment clearance in drains looked to native plants to try and find ways to reduce the sediment loads entering the streams, and tested and over time developed not only biodiversity toolbox, but actually, different tools, more than 14, that could be accessible and useful for farmers. And these are just examples of the kinds of community engagement, policy engagement, farmer engagement that happened in that period. So we were able to generate a toolbox that looked like this stack tool that Merrin was just talking about, having tools at the edge of the field, such as the bioreactor, which was useful for nitrogen, which was the nutrient of concern there. Really rethinking this water's edge, can we rethink this riparian area to be more functional? And then if we need to, move within the channel margins. And so I think only through this sort of partnership and network of a number of different farms were we able to get to this question. And so this is just a photo example of what that looked like. So this was a typical farm. It could be, here in Southern Ontario. When we pulled back the banks, I know we're dealing with Phragmites in the Great Lakes. They're dealing with monkey musk and watercress. communities were able to participate in one particular trial that was looking at a plant-based approach to drain maintenance. The biodiversity benefits that occurred came within a few years. These plants were starting to self-seed. We were starting to see, the plants that were used were very efficient at taking up things like nitrogen. And then there's no further requirement for doing any dredging in this waterway. And, biodiversity has returned pretty quickly. So again, if we can think about the multiplicity of outcomes and benefits, I do think that there might be some made in the Sydenham River watershed solutions that we can explore. But what really gives me hope is that this approach has been written into district council policy. So as of last year, this approach of thinking of a toolbox approach for looking at agricultural waterways is something that we're starting to see as wise practice, and that can only be achieved through partnership. So I hope that you have some ideas of things that we are doing, the data that we're using to inform it, and the stories that we're trying to tell and engage with one another to try and have a deeper understanding of what might be some good ways to form partnerships locally. We do need more empirical science on the ground, and again, at the scale at which and in the ways at which our watersheds are really big, and there's lots of different ways to achieve conservation outcomes and farming outcomes together. I hope that we can continue to work together in this way. So I'm happy to answer more questions. And again, thank you for the opportunity to present some of our work.